So let's just go ahead and start off with your background. Maybe tell us a little bit about yourself.
Yeah, my background. So maybe very short. I grew up in Germany. I started getting into video games, and maybe because of that, I also started getting into programming rather early during middle school, high school. So I started doing a bit of C, C++, a bit of web applications, and then decided to study computer science in Germany. Basically, you do like a bachelor's and master's. That's what usually is expected. And I enjoyed my time. I learned kind of a lot of different programming languages. I learned, very broad set of computer science skills. And towards the end of my bachelor's or undergrad, I doubled much more into kind of applied mathematics, and I was looking for, kind of the harder courses that the university had to offer. And eventually I ended up in the computer vision and machine learning area. And also started doing research there on back then a topic called superpixel segmentation, which was basically image segmentation. Not a lot of deep learning there yet. This was basically my first exposure to research, and I continued that with throughout the master's. Eventually, decided to do a PhD, and then during my PhD, I basically got introduced to, deep learning, various topics. And towards the end of my PhD, I did an internship at DeepMind back then, and joined full time after finishing my PhD. And I've been at DeepMind or Google DeepMind now for 3.5 years roughly, working on a range of different topics, ranging from multimedia watermarking to AI for health to statistical uncertainty estimation for deep learning, among others. So yeah, I think that's a very short summary of my background.
Awesome. Okay, so let's go ahead and backtrack all the way to the beginning here. So you're an undergrad. As you mentioned, you sort of had some sort of background in programming. Maybe tell us a little bit about kind of like your interest in research, like why specifically research from the get-go. I mean, I'm sure you were probably considering, software engineering, some of these other different sort of tracks. Like what kind of like really like excited you about research?
Yeah, I think there are a couple of factors. So I was actually very much into software engineering during my undergrad. I also did internships at kind of a few companies, among others in the automotive industry, but also at Microsoft. And I enjoyed software engineering. I still enjoy software engineering these days. I think software engineering is a big part of research, especially in deep learning and generative AI. During my undergrad, I basically got into, so we had to choose kind of a minor essentially at the university where I was. And I chose mathematics because, I like mathematics. I like kind of the more formal nature of, making progress. And I think this introduced me to kind of a world that's, in between computer science and applied mathematics. And I very, very quickly got interested into topics that kind of surround machine learning. This was a bit before, so deep learning was around, but it wasn't really called deep learning yet. And it wasn't very that relevant, especially in computer vision. But I think this then pushed me a bit into the research direction. So I was kind of taking courses on machine learning and computer vision and kind of applied math. And in one of the courses, the professor offered essentially kind of student researcherships. That's where I started getting into research. I did my kind of bachelor thesis there. And I think I just enjoyed this overlap of kind of fairly interesting kind of mathematical foundation of kind of a lot of these machine learning methods, while at the same time very practical in the sense that you have to get these models running, you have to kind of work with kind of different types of data, such as images or text, or later in my PhD I did kind of 3D work. So this is one thing that I think got me very excited about it, despite it being kind of the more challenging part of my undergrad. But then also research I sticked around because I think just because of curiosity, I just wanted to learn a lot. So I started reading more papers. I started getting kind of excited about different ideas from papers. I started, my first steps of, building on top of different papers, implementing papers and so on. And this ultimately led to the fact that, I continued doing this for my master's. And then at the end of my master's, I thought about what I want to do. And the industry, especially in Germany at that time, in the computer vision and machine learning field wasn't that big. So there were just way more opportunities to do this kind of research and this type of work in academia. And I think that's kind of one of the main reasons I sticked around, besides, of course, the fact that I found a great kind of PhD position, and I kind of found a great PhD advisor, which obviously also contributed to it. But I think in the end, it's just some sort of curiosity-driven. So I like to challenge. I like to read papers, be state of the art, try to implement papers, have more challenging also mathematical problems at the same time coupled with very practical software engineering kind of problems. And yeah, this ultimately led to me deciding for a PhD, and the rest is history.
Tell us a little bit about how you figured out like exactly what research direction you wanted to pursue for your PhD, and then also like picking an advisor is a pretty nebulous decision for most people. Like,
Yeah.
how'd you end up like picking your advisor, stuff like that?
Yeah, very good question. So I think the research direction was to some extent random. So I ended up very early in computer vision, and this was mainly due to at the university where I studied, I enjoyed the computer vision lectures a lot. So a lot of the machine learning that I actually learned doing my undergrad was actually as part of computer vision lectures, right? So this was the first steps of neural networks, but also more like classical machine learning like SVMs, logistic regression, and random forests, and so on. And I actually learned about these techniques in the computer vision lectures. And then, this ultimately led to the fact that I started, doing research at this kind of computer vision lab at my university. And I think this was the main driver of me getting into computer vision at that time. There might have been other factors, just, lots of good friends of mine also kind of ended up in computer vision. So there's kind of some group dynamic as well. Also, there wasn't really a big machine learning department at the time. We had a computer vision department, we had a kind of natural language processing department, but no general machine learning group. So I think all of these contributed in the end to me going into computer vision in the beginning. But I think a lot of these things, as you can tell, are just random to some extent. The people I interacted with, the lectures I heard, the professors I liked, the opportunities that were presented to me.
Mm-hmm.
So that's to the question of choosing my topic, and then for choosing an advisor, I think there's also an element of randomness, just in terms of timing, kind of which labs and which groups are looking for new PhD students at a specific time. In my case, I essentially did my master thesis at the Max Planck Institute for Intelligent Systems in Tübingen in Germany. I had a great time there, and then I basically had another opportunity at another of the Max Planck Institutes in Saarbrücken. I decided to go with the latter, and I think both decisions would have been fine. There was a bit of a personal constraint that I wanted to kind of stay in the vicinity of where I grew up originally. But in terms of looking for a PhD advisor, PhD advisor, will have a lot of influence over you working a PhD, and you'll spend a lot of time together. And I think there are a lot of different concerns and questions that I'm not sure if it's worth going into. I think I actually had a blog article about this a while back. But in my personal case, it was really that I found a PhD advisor that I've found I can learn a lot from, not only on the technical side, but especially on also the personal side in terms of kind of personal growth. And that I think was the main reason that I ended up kind of going with this particular PhD program. I think the secondary factor was probably that I was given a lot of freedom. So I could basically I could look into a lot of different problems. In the end, I ended up working on, deep learning robustness, adversarial examples of distribution generalization and these topics. But it was up to me to find a topic that I was excited about. And I think the combination of the two of, finding someone that I feel I can learn a lot from and having some freedom in choosing what to work on, I think for me made a real difference. Not sure if it was the kind of best decision in the end. I mean, you can't make the counterfactual, but for me, these are definitely the two important factors, I feel.
Mm-hmm. Awesome. Okay. And then sort of like moving forward past that, maybe just tell us a little bit about like how you kind of got introduced to DeepMind. I think you sort of alluded to this a little bit earlier, but like how did that whole process end up? And then also just like at a high level, if you can discuss kind of your trajectory at DeepMind, like, to the extent you're comfortable sharing, like how did you end up deciding which topics to work on? It sort of sounds like you worked on a few different topics, like AI for health,
Yeah.
so on and so forth. Like, how did you end up getting into those topics, or even interested in those topics, or even working on those topics? Was that also just like more serendipity, or just like maybe kind of walk us through that path?
Yeah, very good question. I think a lot comes down to, what you call serendipity or, curiosity. Essentially, I applied for an internship in end of 2019, actually. I applied to kind of multiple different internship programs. And in the end, I decided I found kind of an amazing host at DeepMind and decided to do kind of an internship at DeepMind. Now then COVID hit, so I applied end of 2019. I was supposed to do the internship in 2020. Obviously, we had the global pandemic. Companies were reacting in kind of different ways. Also, doing a PhD in the global pandemic was not trivial. So the PhD, the internship was shifted a year later. So I actually did the internship in 2021 remotely in with the same team and the same host that I originally matched to. And I worked on uncertainty estimation for deep learning. Back then, kind of conformal prediction, which is a specific statistical framework to do uncertainty estimation, became very popular. And I basically tried to figure out how you could integrate that into deep learning in a meaningful way. And I really liked the internship experience. I liked my host. I liked the team. The team I was in actually worked on very similar topics that I worked on during my PhD. I think at that time it was probably one of the more visible industry labs that in Europe that worked on topics that I was interested in and that I had experience in. So it all fit together very nicely. And at the end of my PhD, I basically asked whether I could come back full time after my PhD. And after a bit of back and forth, that actually worked out thanks to a lot of people that supported me and advocated for me. And then I finished my PhD in the meantime, and I came back in 22. So that's roughly how I ended up at DeepMind. And then in terms of topics, it's been very dependent on essentially the people I worked with. So I started working on statistical uncertainty estimation for deep learning, and the applications we worked with or the people we interacted with, we're working a lot on health, on AI for health. So we looked into applications on the health side, and that's then what I continued when I basically started full time. So that's where the health element comes from. It's just that a lot of the people we worked with and a lot of people in the team worked on AI for health. So it was a very natural choice. But I'm actually quite happy that I stumbled over this, because I think health is an extremely can be an extremely impactful application. I think it's an extremely exciting application. It's very interdisciplinary work. Like every day, I kind of talk to clinicians or other people from the healthcare system, and kind of I just learn much more, and it changes my perspective on how I do machine learning and deep learning research as well. And then so this was the health work, and then some other things I worked on over the time was watermarking. So watermarking is essentially embedding imperceptible signal into generated content. Think about generated images, generated video, generated audio, in order to then detect it. And our team basically shipped a product called SynthID, which is Google's watermarking solution. So that's what I worked on for a while. And then I basically went back to, or I wanted to do more work in health again. And at that time, LLMs were getting big. I worked on MetGemini, which is kind of Gemini models applied to health. And now more recently, we extended this essentially to, AI agents for health, trying to figure out whether you can have medical consultations with AI agents. So overall, the health thing was a bit by coincidence, but I think a very, very lucky coincidence. And then the watermarking work just continued my topics from my PhD. So in my PhD, I worked on, robustness to adversarial examples, robustness to distribution detection. These are all topics that are extremely relevant for watermarking, because the watermark you embed in the generated media, you want the watermark ultimately to contain as much information as you want, but at the same time also be robust to not only adversarial manipulation, but also random manipulations of you downloading the images and changing the compression, or you resizing the images, or you kind of editing the image in some way. So I think it puts it very well together. So the watermarking bit basically continued work from my PhD, and then the uncertainty work that I did during my internship kind of morphed into work on health AI, essentially.
Mm-hmm. Got it. Very exciting. Okay, cool. So, throughout your sort of, I guess, time at DeepMind, and maybe like the latter half of your PhD, do you want to highlight any papers that you're particularly proud of that you feel like you had either A, like a significant contributions to, or B, like were really kind of like shaped your journey as a PhD student? I mean, I think generally like there are, especially in your early career as a research scientist and being like sort of being at a PhD student, there are generally like a few papers that were like really difficult to get done, but people are very proud of. Like, what were sort of those like milestone papers for you?
Yeah, that's a very good question. So I think I had a few of these during my PhD, and they're all connected to robustness of deep learning models. The first paper was about this was basically my first paper. So I did in the very beginning of my PhD, based on my master's thesis, I worked on um, deep learning for 3D reconstruction, and then after finishing this, I basically sat there, and that's what I mentioned earlier, that I basically had this freedom of choosing my PhD topic. So I sat there and I was getting really, really excited about understanding why deep neural networks fail in very, very unexpected ways. And I saw this in this work on 3D reconstruction. So I sat there and thought, okay, like, can you do some work on this? And luckily around this time, people started discovering what's called adversarial examples, right? In images, these are like very, very small perturbations that cause misclassification of your network. These days, very similar concepts would be jailbreaks of LLMs or prompt injections or these kind of things, right? So it's basically adversarial manipulations, very targeted manipulations of your input that cause unexpected or adversarial behavior of your model. And I found it very interesting. And so my first paper, or I started a series of papers, the first one trying to understand, hey, if we can improve the robustness against these manipulations, why do we actually lose accuracy? So usually if you train your model to be more robust to, for example, jailbreaks or back then adversarial examples, what we observed is that you reduce your accuracy of the model. And I did a series of papers on this. The first one just trying to understand and benchmark and evaluate what actually happens. And then two more papers, one paper trying to fix it, which I think was one of these more challenging papers, where I initially thought that, this is a really, really nice idea. And then it didn't work out as well. And it really took a year or so to get it working. And specifically there, we try to, train neural networks on adversarial examples. But instead of, usually what you would do in so-called adversarial training is train neural networks on these adversarial examples to improve the robustness, to basically teach the model that even though the input has been manipulated, you're still supposed to predict the right label or do the right action. And I basically thought about, hey, if these adversarial examples are so difficult to get right, we can just teach the model to, abstain on predicting on these examples, right? Just give us low confidence, tell us that, you don't know what the answer is. And this sounds like a very easy idea, and I think there was quite a bit of follow-up work on this. But it was quite challenging, and this really took, 1.5 years of my PhD. So I'm very proud of, having gone through this experience of, reader research where you kind of have to try a lot of different ideas to get to something that works. So that's during my PhD, and then in the beginning of my time at DeepMind, I think some of the work I'm proud of that I think is a bit underappreciated, but getting more and more attention recently in the context of LLMs is we worked a lot on rate of disagreement, kind of trying to understand, even before LLMs became popular for classification models, for example, if your raters, like, if they disagree, then how do you actually get reliable ground truth, right? So machine learning, we are used to having data sets of, inputs and outputs, and the outputs usually being labels or some ground truth, segmentations or some ground truth answers. And we usually take this ground truth for, being the truth, as the name says. But in reality, of course, all these ground truth values are derived from human annotations, right? So in all these big data sets like ImageNet or all the big text data sets, somebody sat down and manually annotated these images or these examples. And if you go to more and more challenging tasks, especially in health, you find that this annotation process is non-trivial. It's actually quite difficult, which means that if you have multiple people do the same annotations, annotate the same images or the same examples, they may actually disagree wildly. And we saw this so this is well-documented fact. We've known this in both in natural language processing and computer vision for a while. But I think in terms of how you benchmark models with it and how you develop models in kind of appreciating that there is this rate of disagreement, is quite tricky. And we particularly saw this in health, right? So we worked on dermatology, where you have skin condition classification. So you give one or multiple images, you ask, hey, like, what's the underlying skin condition? And you have different dermatologists, right? Like highly specialized people that went through like decades of training. And they still disagree widely. And the disagreement they have can be quite nuanced, right? Because you don't have they usually don't give you a single condition, but they give you a so-called differential diagnosis, right? Like a range, like a list of possible conditions. And then if you have multiple of these lists, trying to, majority vote them of some sort can actually be quite tricky. And then even if you do a majority vote, right, you decide, hey, like I resolve this agreement and I declare this one condition as my ground truth, then training against this condition and evaluating against this condition actually ignores a lot of the richness of the underlying ground truth and the underlying annotations you have. And so we did some work on, understanding this, building statistical models to properly evaluate models in light of this disagreement. And so I'm quite proud of this because it's still a bit of a niche topic, but I think in the realm of language models and multimodal language models and so on, I think people are more and more appreciating that in many of the tasks that we tackle, or in many tasks that we expect AI agents or LLMs to perform well, there is no single ground truth. These are very ambiguous and difficult tasks. Even experts that have been performing these tasks for ages are in disagreement about what's the right thing to do, what's the right label, what's the right action, and so on. So I think that's quite interesting. And then maybe finally, one thing I'm very proud of is our recent work on Amy. Amy is an AI agent to simulate medical consultations. So basically, if you go to your PCP with a new symptom, can we kind of have this consultation that you would have with your PCP with an AI agent? And more importantly, how do we actually evaluate this? And there was some prior work on this from the team I worked with. And then when I joined the team, we tried basically to figure out how can you, if you were to deploy such a system, how could you do it in a safe manner? And how could you build in some sort of expert oversight that clinicians and PCPs can basically oversee the system? And we did a big rater study, basically simulating the whole process, doing oversight with real clinicians, and found some kind of very interesting insights actually that maybe we can go into. But I think these are kind of three things that I'm quite proud of. All of these have in common that I think they were challenging nonlinear projects where we started with a particular idea, but then the more we learned and the more we tried, the more it changed the project, which I think makes for very, very exciting research projects.
Awesome. Okay, let's go ahead and get started with the more technical part here. Let's start with this Amy stuff. Super important stuff.
Yep.
For the audience, context on this, like, Google Research has a blog, as do many companies. One of these blog posts is titled "Enabling Physician-Centered Oversight for Amy," and so obviously David was involved here. Now I think there's a lot of exciting problems to sort of discuss here, but like maybe one that's super exciting, especially because this is in the healthcare domain. It's sort of like how you go about evaluating something like this, and also kind of the more real world aspect of this. I think, quoting the paper verbatim, it says, we conducted a virtual OSCE study to contextualize GME's performance across 60 case scenarios developed by an OSCE laboratory. And then you have this study that includes patient actors, GME, and two control groups. And these control groups are either PCPs with 5 years or less of independent practice experience, as well as like a group of NP/PAs. So maybe just tell us a little bit about kind of like how you went about the design, like just designing the scientific experiment here, and then we can get into some of the more technical stuff as well.
Yeah, that's an amazing question, and I think that's kind of the core contribution of the work, or kind of the core difficulty. So maybe for a bit of context, so Amy is our name of this AI agent that performs medical consultations. And we have in previous studies shown that this actually works quite well. So compared to PCPs, these are like our AI agent, very often has good diagnostic performance. Patient actors like it in terms of, how it does the dialogue, how much empathy it shows, and so on. Obviously, there's a lot of disclaimers for this work, and in our work, we always try to, we are not, like, our goal is, of course, not to replace doctors. And being a doctor and a PCP is much more nuanced than this kind of very, very limited, very niche evaluation that we do in the paper. But still, these models show promise in these tasks. And we basically tried to build in oversight. And as you said, evaluation is kind of a core crux of the whole thing. So the first thing you mentioned is that usually what we do is these so-called OSCE studies. OSCE basically stands for, I think, Objective Structured Clinical Examination. It's a fairly standard exam that doctors and medical students go through, in which they have simulated consultations with patient actors, very similar to what we did in our study, and then are evaluated on different rubrics, basically evaluating diagnostic performance, but also evaluating the style they conducted the consultation in, right? So, for example, did patient actors have the feeling that they connected with the doctor? Did patient actors feel that the doctor was empathic? Did patient actors feel that the doctor was trustworthy, and so on? So a very, very wide and fairly nuanced evaluation. We call these usually different rubrics. So we have these different rubrics for different parts of the evaluation. For example, the diagnostic part, the patient actor facing part, the history taking part, where history taking basically means, do I ask the right questions? Do I get the right information from the patient or the patient actor in this case? So in our case, because we had this oversight component, we first asked patient actors to basically have a consultation and a discussion with our AI agent, Amy. And Amy was basically asked to, take the history, understand the patient's concern, ask the right questions, understand medical history, and so on. But we constrained Amy to not provide any individualized medical advice. So Amy was told that under no circumstances, and we had kind of a guardrail mechanism to make sure of that, that it shouldn't share any diagnoses, it shouldn't share any treatment plan, it shouldn't share any, individualized kind of medical information for the patient. But then after the consultation, our agent basically kind of provides a summary. The summary was provided in the so-called SOAP note format. SOAP note format, for those not familiar with medicine, it's just like a summary of the case. But in medicine, SOAP note is a very standardized format of how you summarize patient interactions, essentially. And then we had these SOAP notes reviewed by kind of the overseeing PCP. So doctors basically looked at the SOAP note and checked, okay, like, is all of this correct? Do I want to make some edits here and there? And in the end, they had to decide, hey, am I happy to share the diagnosis with the patient, or do I need to have a follow-up consultation? Which basically means that Amy didn't do a good job in, asking the right questions, understanding the patient's case, and so on. And we basically did this with Amy, but we also had the two control groups you mentioned, the one control group being other PCPs, and the other control group being nurse practitioners and physician associates. And so this latter group, nurse practitioners, physician associates, are basically known as physician extenders. These are roles introduced in different healthcare systems across the globe, including many US states, that can independently perform these consultations with you as a patient, but are very often operating under oversight or under supervision. So in the end, they're supervised by kind of a PCP or a physician. And that's why we took them as control groups. So we did the same. We asked them to have the consultations. We asked them to, write a summary note. Then we asked the overseeing PCP, where PCP, by the way, means it's a primary care physician for those not in the US, to basically review the case. And then in the end, we basically asked, again, independent physicians to look at all this information, look at the transcript of the consultation, look at the SOAP note, the summary, look at the edits that the overseeing PCP did, look at all the decisions involved, and basically evaluate all of this information across all of these different rubrics that I mentioned earlier, right? So we had rubrics that we had in prior work already, so, about the diagnostic quality, about, the history taken during the consultation, about, empathy and, report building and, trustworthiness of as perceived by the patient actor. But of course, we also added additional rubrics. And then across all these rubrics, you basically have independent physicians rating these rubrics, and that's where you can basically compare. And again, also connecting that to my previous work, of course, there is disagreement, right? So one concrete example is we had these transcripts and we asked the AI agent not to give individualized medical advice. But then if you evaluate this, physicians actually disagree on what constitutes medical advice or not, because it's a very nuanced topic. It's very context dependent. So you have this agreement that you have to deal with. And then, of course, the sample size is fairly low. We did this for, I think, 60 different scenarios across Amy and the two control groups. So this is roughly how we evaluate it. And then you can, based on these rubrics and these kind of ratings, you can then see kind of trends. Very often you can't see something statistically significant because on many of these rubrics, both Amy as well as the physicians and the nurse practitioners actually perform fairly well. But on some axes, we can see, okay, the AI agent actually performed better than the two control groups, and you can evaluate this in a statistically significant way. And this is essentially how we evaluated this. And then in practice, of course, this involved a huge data study where you have to schedule all your patient actors to have sessions and have consultations with Amy or physicians, right? Then you have the second step of the oversight step, where again you need to put all the information into a nice UI that we prepared for this task, for them to edit all the notes and so on, and then in the end you have this evaluation. So this was kind of quite a long process that took us more than roughly a year to plan, and then probably half a year to 3/4 of a year to actually execute on. But I think it shows a bit the promise of what AI agents in health can do.
Mhm. Yeah, absolutely. Sort of moving forward, another paper that you worked on, I believe, is titled Med Gemini. And so this is just kind
Yep.
of a much more general project as well. Maybe just tell us a little bit about this. I think most people in the audience probably know what Gemini is, but maybe they don't know a ton about Med Gemini. What do you think
Yep.
was, wait, maybe like, because this is a pretty big research project, what do you think is specifically like the area that you were working on to the extent that you're allowed to talk about?
Yep. So MedGemini is basically a family of Gemini-based models that were, fine-tuned or adapted specifically to the medical domain, and then we basically showed on a wide range of different benchmarks, reaching kind of from ranging from simple, medical question answering like, medical licensing exams, like questions like MedQA. MedQA is kind of the corresponding data set to, more multimodal tasks of, image understanding and so on. We basically showed that this family of models performs at the state of the art, outperforming many previous models. So this was kind of the scope of the project and also the goal of the project. The goal of the project was essentially to show, the capabilities of Gemini in the health domain. And I specifically, again, connected to this story about racial disagreement, I worked on this data set called MedQA. MedQA is, I would say, one of the focus kind of data sets or benchmarks where very often if you look into medical AI systems or medical LLMs, this is kind of the central benchmarks that people compare on. MedQA basically consists of, among others, a set of questions that are in the style of the US medical licensing exam. However, these questions, of course, have been obtained over multiple years and have been scraped from different web pages. And models basically started to separate on this data set, right? So improvements from model to model kept getting smaller. So one thing I looked basically into is how meaningful is it actually to evaluate on this data set, right? So are all the questions correct, actually? Are all the answers correct? Are some of the questions maybe outdated and so on? So we again did a quite big data study with physicians asking them, hey, this question, can you answer it? If you answer it, do you agree with each other? If you don't answer it, do you feel there is kind of some missing information? Do you think the information is outdated and so on? And this allowed us then later to basically go back and say, okay, this is the accuracy we get on MedQA as is. But now if we filter out questions that we think are unfit for evaluation for various reasons, then the performance actually improves a bit. We can also quantify the uncertainty around this, right? We can quantify, what kind of variation would we expect models to have on these questions. And yeah, in the end result for MedGemini was that we had a new state of the art on MedQA, but we also had these new labels for MedQA where we basically say, hey, like we believe that some questions are outdated, some questions are not correct. There are some labeling errors here and there, and we would prefer the community moving forward to use kind of this more nuanced data set with our new labels. So this was kind of a key contribution that I did to MedGemini.
Awesome. Okay, moving forward, there's a lot of other really exciting research that you did that you've been working on. You worked on some things with like SynthID. You've worked on some things with kind of as we talked about Amy. Maybe tell us a little bit about kind of the separate. So I think we spent a lot of time with sort of AI for medicine, sort of that area. Maybe tell us about one of your research directions that's like in a completely different spectrum. What are you most excited about?
Yeah, so I can't talk too much about the research directions in the context of SynthID, unfortunately. But
No
I'm
worries.
generally very excited. Yeah, I'm generally very excited about. I mean, I've co-developed it, of course, but I am very excited about watermarking. I hope that more companies and more frontier labs pick up on it. I think we've seen it kind of multiple times over the last couple of years that it's getting harder and harder to distinguish generated content from real content. And I think watermarking can be part of the solution. It can definitely add more transparency. And I think especially with more of this generative media flooding social media, I think this will be kind of incredibly important. And I think there are quite some interesting challenges. And we recently had a report on SynthID Image, which is kind of the image watermarking, which goes into many of the challenges that we faced in deploying these systems at internet scale, right? Like really processing like billions of images. And I think there are extrapolating from this quite some interesting challenges on how you can come up with a watermarking standard that works across the industry and that really um, fulfills the promise of using watermarking to add more transparency in generative media. So that's something I'm quite excited about outside of health. But then, irrespective of this, in the context of LLMs, for example, I'm incredibly excited, for example, about reasoning as well. In health, we saw it over and over again that base models are getting better and better. And I think a big part of that is that we figure out better ways of, scaling reasoning or scaling models in general. But these days, it's of course a lot about reasoning. And I think this will open much more applications, not only in the health side, but also in many others.
Awesome. And our very, very last question, because we're getting very close to time here.
Yeah.
What is the bottleneck left for medical AI? Do you think it is the reasoning models getting better? Do you think it's the actual application of integrating them with subject matter experts? Do you think that there are
Mm,
other things? Do you think there's hesitation among said subject matter experts to adopt AI? Like what like if you had to sort of rank in descending order like a few of the different
yeah.
bottlenecks that you've observed, what are they?
Um, it's hard to rank, but I think for me, the top two would be trust and integration. So I think essentially one of the main problems is healthcare is not healthcare. Healthcare varies a lot, not only by country, but even by different hospitals, by different providers you walk into in the same system.
Sure.
Not even to talk about, physicians' individual preference, different countries, different regulatory systems, and so on. Um, there's extremely wide variety of workflows, and I think integrating AI properly into workflows will be extremely important, but it's also difficult, right? It's basically imagine it's a bit the analogy to integrating AI coding systems into our IDE, into our code review systems, and so on, right? Like the workflows that we work with daily as engineers or as researchers, all right? Of course, we know these systems, so for us, it's kind of easier to integrate them. Also, programming languages are fairly formalized, easy to work with. But now you need to do this in the healthcare domain where workflows vary extremely widely, and you have, of course, much more stricter constraints in terms of patient safety, for example, but also in terms of, and that's the second point I mentioned, trust, right? I think patients, clinicians, physicians, providers, insurers, and so on will adopt AI much more easily if we as well, like if the health AI community can convince people that they are safe, but also that they're trustworthy, and that we have proper ways of citing, for example, or following kind of guidelines. Also something we worked on for Amy, how to follow kind of common guidelines in healthcare. So I think for me, these are the two. I think there are health-specific capabilities that will remain important. I think general purpose models are getting better and better. This includes performance on health. But I think it's still important to benchmark them. But of course, then beyond that, you have a lot of specialized domains where specialized model might have a place. So I think capabilities is in my view, a bit less important. So I think there are already applications or impact that we could have in the healthcare system that would be possible with today's models. But I think properly integrating into the healthcare system so that it becomes, a win-win situation for everyone, or win-win-win for, physicians and patients and, us as model providers. I think that's the main challenge.
Awesome. Without further ado, thank you so much for coming on the podcast, David. Really appreciate your time.
Yeah, thank you for having me. It was a great conversation.